All right, so our last topic that we dealt with on the last time we met on March 16th was L'Hopital's rule, and we very briefly introduced it. And again, pronunciation on that is L'Hopital. It's a lot of stuff going on in that particular name. That's just an individual's last name. So L'Hopital is the last name of a mathematician, and he's got actually an interesting backstory, but we'll focus on just the mathematics for the time being. So L'Hopital's rule has to do with limits. And so when you're being asked to take a limit, and we've taken plenty of limits this year, but L'Hopital's rule has to do with limits. And specifically limits in this thing we talked about called indeterminate form. So indeterminate form. The main indeterminate forms are when you have a limit that presents as infinity over infinity or 0 over 0. Those are like the big main uses or main ways in which we see L'Hopital's rule get used. And we saw a number of examples in the last time we were in class together. But just look at this, because we've certainly seen this idea before. So if we have the limit as x approaches infinity, and it can be x approaches anything. It doesn't have to be infinity. It could be 0. It could be a number other than infinity or 0. So it's just x approaching something. And we'll look at some examples where it's not infinity. But if we have something along these lines, x squared minus 1 over 3x squared plus 1, and we're sending a limit of x to infinity, what we're saying is, okay, take a look at this function. What happens when x gets really, really, really big? And if you just straight away plug infinity in, you're going to get infinity up top, and you're going to get infinity on the bottom. So you're going to get big over big. And the truth of the matter is these bigs aren't created the same. They come from different things. But to judge infinity over infinity on its face, we can't do. And so we have to have some way to adjust it. This one, actually, we have a way to adjust, and I think actually did this problem much, much earlier in the year. We had an algebraic strategy on a problem like this. So some of these, we've seen a kind of a subset that you can do using an algebraic strategy where we divide by the highest power. So it's kind of this neat thing where we say, okay, let's take the highest power in the denominator, and let's divide every term by that highest power. So in this case, that's going to be x squared. And it's a little cumbersome, but when we do it, these first two terms are going to simplify nicely for us. So let's just kind of get some more space. We have 1 minus 1 over x squared, and then these first two terms, or that first term on the bottom, is also going to simplify nicely. And the reason the dividing by the highest power works when you're going to infinity is anything that still has an x on the bottom, when you put infinity in, it will go to 0. This is a unique trait when we're going to infinity or negative infinity. In other words, it works really, really well with power functions going to infinity or negative infinity, a specific subset of L'Hopital's rule. L'Hopital's works for any infinity over infinity, including this one. But you can do this one algebraically. We have, when we put infinity in, now we get 1 minus 0 over 3 plus 0, and we get 1/3. What that 1/3 means is the infinity on the top and the infinity on the bottom have a 1-to-3 ratio. In other words, that one on the bottom is 3 times the size or 3 times the bigness of what's up top. And we can see it when we actually divide by the highest power. So that's one way to do it. L'Hopital's offers another way. So L'Hopital says instead, if I take the derivative of the top and the derivative of the bottom separately, not the quotient rule, just look at the derivative of the top. So look at the derivative and look at the derivative of the bottom. And compare the derivative, or compare the rates of change. Well, the derivative on the top is 2x, the derivative on the bottom is 6x. Here we still, if we were to put infinity into this, we'd still have infinity over infinity. But you can do this a number of ways. You can recognize that, hey, you know what, the x's actually cancel and I'm left with 2/6. Or if you were so inclined, you could take the derivative a second time. And you can take as many L'Hopital applications as you want. Derivative on the top is 2, derivative on the bottom is 6. So you can either get here algebraically or reapply L'Hopital's rule, and you end up getting 1/3. We get the same result. What we're using, though, is this alternate way of analyzing the limit that involves taking the derivative of the numerator and comparing it to the derivative of the denominator. And that's what's at the heart of L'Hopital. So again, it uses derivatives. So L'Hopital, let's write it down here. L'Hopital uses derivatives, but it in and of itself is not the quotient rule. So it uses derivatives, and you're just comparing the top versus the bottom in terms of their rates of change. So if you can't say what this top infinity is versus this bottom infinity, then what you say is, well, how are these numbers changing? And then if you just apply that rate of change to infinity, you would have a sense of how much bigger the one infinity is than the other. So it's just kind of an abstract thought process of saying what's happening to these really big numbers. If I can't say what they are, if all I can see is that it's infinity over infinity, maybe I can say what's happening to them. And the happening, or the rate of change, is what L'Hopital's rule is measuring. So L'Hopital's rule uses derivatives to analyze indeterminate forms. So analyze 0 over 0 or infinity over infinity, which are called indeterminate forms. Indeterminate. That one always gets me on spelling. Indeterminate forms. And it's a useful tool. That's only one application of it. And the formal mathematics says if we have a limit as x approaches a, so any number, a, of some function over another function, that's the same thing as if we look at the limit as x approaches a, oops, that should be an a, as x approaches a, of the derivative of f over the derivative of g, provided that we're talking about something that's in indeterminate form. And L'Hopital's rule does not work effectively if we don't have indeterminate forms. And we'll see an example of that here in a moment. So again, have to have indeterminate forms for L'Hopital's rule to work. So let's take a look at an example where L'Hopital's rule is not needed. We've just seen an example where it could be used. And actually, let's look at an example where it has to be used first. I misspoke. Let's look at an example where it has to be used. So if we have something like the limit as x approaches 1 of x squared minus x over x squared minus 1. If we try the highest power trick here, it won't work. And the reason it doesn't work is when you're plugging in a 1, you're not getting anything to zero out. So that algebraic trick is not going to cut it for us. We can potentially do some other algebra tricks on this thing. We can do some factoring here where we could say, oh, I'll take an x out on the top and I'll split the bottom, x plus 1, x minus 1, cross off the like factors. Now I have x over x plus 1. Now I can plug a 1 into that, and I would get 1 over 2. Or you could apply L'Hopital's rule. So you could use L'Hopital's rule, and you could do oftentimes denote it as LH, just kind of shorthand. You have 2x minus 1 on top. You have 2x on the bottom. And then if we do that for L'Hopital's rule, sorry, I'm just pausing to catch my thought here. If we do this using L'Hopital's rule, when we do 2x over 2x, we end up getting 1. I'm sorry. I don't know where my head's at. So we're doing the limit as x goes to 1. I just missed that little application on there. Just had a momentary lapse of judgment, but that little x goes in there and we get 2 minus 1 on top. We get 2 on the bottom, and there's our half. And I was getting a little lazy. I put this LH in here, and that threw me. I shouldn't have let that happen. I should have just written the limit as x approaches 1 of 2x minus 1 over 2x, and then I would have known what I was plugging in. I just kind of froze up there for a second, but that happens to all of us. So that's a case where, again, we can do some algebraic analysis on it, or we could use L'Hopital's rule. And there are certainly situations where you have to use L'Hopital's rule. There's no other way to it. We saw some of those in class, and these are just some extension examples. So this is one set of things that we can do with L'Hopital. It is the most common set. There are some more uncommon ones. So I'll write uncommon uses. Uncommon uses involve if we have some limit that generates infinity minus infinity. Big minus big, we really don't know much about it, how to do it. That's considered an indeterminate form. We could have 0 times infinity as the output of a limit. Again, here, don't really know what small times really big is. So we could do a subtraction, we could do a multiplication, we could do or have a result that is 0 to the 0 power if we have a limit. That is indeterminate. We don't know what anything to the 0 should be 1 and 0 to the anything should be 0. We could have infinity to the 0 power, and we could have 1 to the infinity. This is a group, the power group here. These are all indeterminate. So if I have something really big and I take it to the 0 power says it should be 1, but the infinity says we should be getting really big. 1 to anything should be 1, but if you take something close to 1 and you send it to infinity, it kind of depends what side of 1 you're on. It's either going to blow up or it's going to get really small. Or potentially if you're close enough to 1, it's just 1. So these are indeterminate powers. This is an indeterminate product. And this is an indeterminate subtraction, or an indeterminate difference would be the appropriate word for that. But you're subtracting two infinities. And these are the other ones you could get. They're very uncommon or less common and less tested on the AP. But it's worth looking at a couple of them just to see, hey, how would we handle these things? So an indeterminate difference would present as something, they'd all present as something that you can create a fraction with. So you might get something like a trig setup. So you have cosecant of x minus cotangent of x. And of course, if you plug a 0 in here, you're going to get cosecant of 0, which is infinity. You get cotangent of 0, which is infinity. Those are both at asymptotes on these two functions. And so you have to come up with some way to rewrite it. And trig functions are really nice in terms that they can be rewritten. Cosecant is 1 over sine, and cotangent is cosine over sine. And when we rewrite that, we still got this limit sitting out here. We have 1 minus the cosine of x all over the sine of x. And we're still going to send the limit to 0. And then we're going to plug our 0 in. And on top, we'd have 1 minus cosine of 0 and 1 minus cosine of 0. What would that be? That would be 1 minus 1, which would be 0. And on the bottom, we have sine of 0, which is 0. And we've got this nice indeterminate form for L'Hopital's rule. So again, just rewriting the trig function gets us this indeterminate form. And then from there, we can now apply L'Hopital's rule. Derivative of the top, derivative of 1 is 0, of cosine is negative sine, the two negatives offset. So we have a sine of x on the top, and then I take the derivative of sine and I get cosine. And again, and this is where I ran into problems on the last one, I got to write my limit right there. So that tells me what I'm going to be applying. So I'm going to put in a 0, and on here, if I put in a 0, sine of 0 is 0, cosine of 0 is 1, and this limit is worth 0. So this infinity versus infinity, that on its face value we can't do. We don't always know what they're going to equal each other. One of those infinities could be much bigger than the other. In this case, they're the same size, and we end up getting 0. So that's an indeterminate difference. An indeterminate product, so that's the other one, the second one that's up here, the uncommon one. And it's the last one that we'll do on this video. An indeterminate product, you have two things that are multiplied together. Again, here, what we're going to be looking to do is to rewrite it as fraction. So we're going to look to write it as a fraction. So an example of this would be the limit as x approaches, let's say, negative infinity. We haven't gone to a negative infinity yet. X squared e to the x. So if we take and put an infinity in here, we get infinity. And then we're going to times e to the negative infinity. So that's a 0. So infinity times 0 is indeterminate. We don't know what that is. So we need to rewrite this thing as a fraction. And we can either write it as x squared over 1 over e to the x, or we can write it as e to the x over 1 over x squared, and then apply the limit. Not all derivatives are made the same. Some of these are easier to take than others, and I'm actually going to use this one. And this takes some trial and error as to which limit you should be using, or which limit makes sense to use. And the reason I like this one is it's just an easier set of derivatives for me to take, and that's just experience. So if you attempted to do this with the other one, you'd run into problems, or it would just become a very challenging derivative to take, and this one just becomes a bit simpler. And we're going to pick up with this particular example in the next video, or part 2 of this particular lesson.